Everyone, and welcome to this explainer. Today, we're diving straight into the universe's ultimate rulebook to see if science fact is, well, actually as wild as science fiction. We're going to take a really close look at the mind-bending physics of time travel, and we'll be drawing directly from the incredibly famous work of theoretical physicist Stephen Hawking. So, buckle up. Let's just skip the pleasantries and ask the ultimate question right up front. Can we really travel through time? For decades, this was strictly the domain of sci-fi writers. Think H.G. Wells or Doctor Who. But here's the thing. When theoretical physicists look at the actual math of how our universe operates, the answer isn't a hard no. In fact, the laws of physics leave the door cracked open just enough to let some absolutely fascinating possibilities slip through. All right, let's start with Section 1, the faster-than-light problem. So, to build a time machine, we first have to tackle the cosmos's ultimate speed limit, which is, of course, the speed of light. There's this famously clever little limerick that brilliantly illustrates a core rule of Einstein's relativity. It goes, "There was a young lady of right who traveled much faster than light. She departed one day in a relative way and arrived on the previous night." It's funny, but it hits the nail on the head. Under Einstein's theory, breaking the speed limit doesn't just make you incredibly fast. Because time is relative to the observer, traveling faster than light fundamentally turns you into a time traveler. To really wrap our heads around this, imagine two events taking place: a 100-meter Olympic race here on Earth and the opening of a Congress on Alpha Centauri, which is trillions of miles away. Now, to an observer sitting still on Earth, the race clearly happens first. But relativity tells us that to an observer traveling near the speed of light away from Earth, the order of these events literally flips. They would see the Congress open before the race even starts. Theoretically, if you had a spaceship that could zip back to Earth faster than light, you could place a winning bet on a race that, to you, has already finished. Crazy, right? Moving right along to Section 2, loopholes in space and time. Okay, so the math of general relativity actually provides a few cosmic blueprints, or let's call them loopholes, for time travel that don't just rely on raw speed. Back in 1949, mathematician Kurt Gödel discovered a solution to Einstein's equations, showing that if the entire universe were rotating, a rocket ship could set out on a journey and return to Earth before it ever even left. Now, observations show our universe isn't actually spinning like Gödel proposed, but scientists found other mathematical loopholes too, like cosmic strings. These are unimaginably dense, ultra-thin objects left over from the early universe. If two of these strings whipped past each other at incredibly high speeds, they could warp space-time enough to allow travel into the past. While these are extreme, highly theoretical scenarios, they do mathematically prove that relativity doesn't entirely rule out time travel. Which brings us to Section 3, wormholes, the ultimate shortcut. If we can't fly faster than light because it requires infinite energy, which it does, we need a shortcut, and we have a theoretical mechanism straight from Einstein himself. Proposed by Albert Einstein and Nathan Rosen in 1935, these bridges are essentially thin tubes connecting two completely different, distant regions of spacetime. Imagine a piece of paper with a dot on each end. Instead of drawing a long line across the page, you just fold the paper so the dots touch and punch a hole right through. Boom, you're there instantly. A wormhole turns a 20 million mile trip into a quick little hop, allowing you to beat a light beam to your destination without ever actually breaking the speed limit in your local space. And as we established earlier, beating light means you are effectively traveling through time. But hold on, let's look at Section 4, fueling a time machine. See, there's a massive catch to our blueprints. Opening a wormhole is one thing. Keeping it from immediately crushing your spaceship is a whole different story. Everything we know, you, me, stars, planets, it's all made of ordinary matter, which has a positive energy density. This positive energy curves spacetime kind of like a sphere, and gravity naturally wants to just crush our wormhole shut. So, to prop it open, we need to warp space in the exact opposite way, giving it a negative curvature, sort of like a saddle. To do that, we require exotic matter with a negative energy density. Think of classical physics like your bank account. You can move money around, sure, but your balance can't drop below zero. Quantum mechanics, however, it's a bit more forgiving. It actually allows you to be overdrawn in certain tiny spots, creating pockets of negative energy, just as long as the total energy of the universe remains positive. And hey, this isn't just some wild mathematical fantasy. The Casimir effect is literally experimental proof that this space-warping negative energy exists in reality. Here's how it works. Even in a total empty vacuum, space is constantly bubbling with these virtual particles, just appearing and disappearing. If you place two extremely close metal plates together, certain waves of these virtual particles simply can't fit in that tiny gap. Because there are fewer particles bouncing around inside the plates than outside them, the energy density inside actually drops below zero. It becomes completely negative. This proves that the exact type of exotic fuel we'd need for our time machine is, in fact, permitted by the laws of physics. Okay, moving to section 5, resolving time travel paradoxes. Let's play make-believe and say we've theoretically built our space-warping wormhole and successfully fueled it with negative energy. We are ready for takeoff. But now we hit a massive philosophical wall. If we can change the past, we run straight into universe-breaking contradictions. Take the famous grandfather paradox. If you travel back in time and accidentally or, purposefully prevent your great-great-grandfather from having children, then you would never be born. But if you were never born, how could you travel back in time to stop him? It's a complete logical nightmare that literally threatens the entire stability of spacetime itself. So how do we deal with this? Physicists basically propose two distinct ways to resolve this paradox. The first is the consistent histories approach. This suggests the timeline is completely rigid. If you go back in time, well, history dictates that you were already there, and absolutely nothing you do can change the present. The catch here? It implies you have zero free will. Your actions are basically pre-recorded. The second option is the alternative histories hypothesis. This is your classic Marty McFly Back to the Future scenario. Under this theory, the very moment you arrive in the past, you branch off into a completely new, separate timeline. You can act freely without destroying your original history, because you're now essentially in a parallel universe.
Finally, let's look at section 6, the chronology protection conjecture.
This brings us to the ultimate final boss of time travel. This concept was famously championed by Stephen Hawking as a way to protect the universe from all those messy paradoxes we just talked about. He called it the chronology protection conjecture. Hawking calculated that the very moment a wormhole is stabilized enough to act as a time machine, those virtual particles from empty space would loop through it endlessly. And because they can pass through instantly, they would multiply their energy over and over and over again, incredibly fast. This massive spike in radiation would create so much positive energy that it would just violently pinch the wormhole shut. Basically, the universe acts as its own cosmic police force, destroying the time machine the exact nanosecond it starts working.
Which leads us perfectly to the ultimate reality check and really Hawking's personal bet against time travel. Think about it. If humans ever do figure out how to stabilize a wormhole and travel through time in the distant future, why aren't we currently overrun by time-traveling tourists? Are they just incredibly good at hiding among us, strictly observing some sort of cosmic rule of non-interference? Or does the chronology protection conjecture hold true, meaning the past is forever locked away, safely protected from our curiosity? It's a question that really forces us to look up at the stars and wonder, just how flexible is the rulebook of our universe really?